Good morning everyone. So today we'll be doing parametric bootstrap using R, and maybe we will try some other things like for example how bootstrap works in the regression setup. Okay. So first let us start with the parametric bootstrap. I hope you remember the theory for it. So suppose I have a sample from normal distribution. Okay. Let me take sample size as say 99. I have a sample from normal distribution with say mean 1 and variance standard deviation also 1. Okay. Now once I have the sample, again we are doing simulation, so I know the distribution, but in real life we are never going to know the distribution. In parametric bootstrap we will assume that the distributional form is known, means I know whether it is normal or whether it is exponential or whether it is uniform, but I would not know mean and standard deviation, or at least one of them would be unknown. So here for the sake of convenience, let me assume variance to be known. Okay, and let us assume that mu is unknown. So we are interested in estimating mu, but we are not going to treat it as mean, we are going to treat it as median, because we know for normal median is also mu. So we will try to estimate it via median and via parametric bootstrap. Okay. So first thing I have to do is get mu from this sample observation. So my mu hat becomes, because I am going to use median estimator, it becomes median of x. Okay. I'm sorry, I have not run this. So okay, so my mu hat is 0.75. Okay, and now let us use this in parametric bootstrap. So in parametric bootstrap what I have to do is I have to estimate parameter from the given data and then use that parameter to generate B samples, capital B samples, and in each of those B samples we are going to estimate the parameter and then see the distribution. So let me take B as 2000. Okay, so every time I would be storing the estimate, so let me call it med star. Now for I in 1 to B, sorry, some of the keys of from my laptop are not working. For I in 1 to B, what I have to do? First I have to draw a sample. So because I know the distribution and because I am using parametric bootstrap, it will be R norm n with mu hat 1. Okay, and then we will compute median for each sample, and maybe I store it in here. So median of S. Okay, so this is what I'm supposed to do in parametric bootstrap. Let me check how the distribution looks like. This is how the distribution looks like, and I can get confidence interval for this median via Quantile. So I can do Quantile med star. I get many. Actually I need only 2.5 and 97.5, and both are not here. So let me give probe equal to 0.025 and 0.975. Okay, so this becomes the confidence interval for the median estimate. Okay, one small point to be noted, this mu hat I have estimated here by median, but it is not necessary to estimate this by median. Even if your final interest is in estimating median and getting confidence interval for it, if you know that mu hat can be estimated better by mean, you can change this to mean. Everything else, this would remain median because your final interest is in median. But this parameter estimation can be by whichever method you know gives the best result. Okay. So this doesn't have to match this. This doesn't have to match this. Okay, remember. Okay, so this is parametric bootstrap. Now we are also interested in applying bootstrap to various situations. So one of them is a regression situation. So in regression situation, there are 2-3 ways in which I can apply bootstrap. So let us see them one by one. First, let us see in theory, and then we will try to code it. Okay. So let us focus on simple linear regression. Okay. Let us focus on simple linear regression. So what is the simple linear regression setup? Everyone remembers, right? So I have n pairs x1, y1, x2, y2 up to xn, yn. I have n pairs. My model is y equal to beta naught plus beta 1x plus epsilon. This is my model. My parameters of interest are beta naught, beta 1 and variance of this, that is sigma square. Okay. You have methods to estimate beta naught and beta 1 and of course sigma square. And then you know the variances of beta naught, beta 1. You can use those variances to get confidence intervals and so on. Suppose I don't remember the theoretical formula, I don't want to use the theoretical formula. Is there any alternative way? Can Bootstrap help me in this situation? So what does non-parametric Bootstrap tell you? Non-parametric Bootstrap tells you have to do sampling with replacement from this given sample. Okay, so this is my given sample. Now I have two variables in my data, x and y. So if I do sampling with replacement separately for x and y, then it's going to be a disaster. Why? Because it may happen that my x2 enters the sample but y2 doesn't. x2 gets paired with say yn. Then the regression relationship would be destroyed. So I don't want that. So first thing you have to do is, when you sample with replacement, you have to maintain the pairs. Pairing needs to be maintained. So this is one way in which non-parametric Bootstrap can be performed in the regression setup. So instead of just arbitrarily doing resampling, what you do is you choose numbers from 1 to up to n, and then those pairs, so ith pair is chosen instead of ith observation. Okay, so you may get say something like x1 y1, x1 y1, x3 y3, x4 y4, x11 y11, something like this as a sample. Next sample can probably be x2 y2, x5 y5, x2 y2, x6 y6, something like this. So the entire pairs you have to make sure you are choosing. Okay, and once you choose the pairs, what do? From each of these samples, you will estimate beta naught, beta 1. So you get beta naught hat star, beta 1 star, and then you take their quantiles to get confidence intervals. In fact, once you have quantiles, you can use them for the testing purpose also, right? So if you want to test whether intercept is significant or not, you check whether the confidence interval for beta naught contains 0. Okay. So this is one way of doing non-parametric bootstrapping regression, but there are a couple of other ways also. So what is the next way? Next way is you have your original beta naught hat, beta 1 hat. So using these, you can compute y1 hat, y2 hat up to yn hat, the fitted values. Okay, so use those fitted values to get the residuals. So epsilon 1 would be y1 minus y1 hat, epsilon 2 would be y2 minus y2 hat, and so on. Epsilon n would be yn minus yn hat. Okay, so we compute residuals like this, and now these residuals we know ideally by regression assumption that all these epsilon i's are supposed to be IID, normal, 0, sigma square. So they are kind of like an IID sample. So we sample these residuals with replacements. So my epsilon 1, epsilon 2, epsilon n, this is treated as an IID sample, and then sampling with replacement is done on this, and once I get new residuals, I can construct new yi's as beta naught hat plus beta 1 hat xi plus whatever is the new residual, epsilon I star probably. Okay, and so xi's would remain same. I won't change my x1, x2, xn, but I would get new, I can call it yi star. So y1 star, y2 star, yn star, and now from these I would estimate beta naught, beta 1, and I would proceed as earlier. Okay, so how would I get new data? I would use original xi's, I would use the original estimates, and I would use the residuals coming from the original residuals via simple random sampling with replacement. Okay, this is another way in which the regression bootstrap can work. Okay, so these are two important ways. So let us try to do these in R so that things are more clear. Okay, so let me first consider say iris data set, and we will try to model petal width and petal length. Okay, so so sepal length, sepal width, petal length, petal width. So suppose I want to model petal length as a function of petal width. So I need third and fourth variable. So my x is fourth variable. So iris fourth column, and y is iris third column. Okay, so let me draw a scatter plot. Okay, it looks more or less linear, so probably linear regression would be a good idea. In fact, I can try the model. So lm y tilde x, these are the coefficients, and summary of model can give me r square. So R square is quite good. Adjusted R square is 92.66, so it's quite good. I won't go into the residual assumptions as of now because our main aim is to see how Bootstrap works in regression. So we'll assume that everything else is going through. You can show the line here. See, this is the line of fit. Okay. So now I have estimates. Let me store them somewhere. So beta naught is f dollar coefficients 1 and beta 1 is f dollar coefficients 2. Okay. So this is intercept, this is slope. Now, as I said, we have two ways. One is doing simple random sampling without with replacement on pairs, or doing simple random sampling with replacement on epsilons. Okay. So let me do on pairs first. So what I'll do is, for again we will use b equal to 2000. We have already defined it, but I need to store both beta naught and beta 1. So let me construct a matrix with n row equal to b, n col equal to 2. For I in 1 to b, what I need for I in 1 to b is my first I need to draw sample from pairs. So what I'll do is I'll sample the indices and then I'll choose pairs corresponding to those indices. Okay. So my n is going to be n row of, or length of x. Length of x. Okay. So my n is 150. Now I need a sample with replacement. So I take a sample from x and size. So I need a sample from 1 to n. Of size n and then replace equal to true. Okay. So I will get indices and then I have to pick up x and y corresponding to those indices. So I will define x star as x at those indices and then y star as y at those indices. Okay, I have x star and y star, and now I have to fit a model again. So f star is lm y star tilde x star, and then b mat ith row would be f star dollar coefficients. Okay, let us try this for first I. Replace, my p is missing. So let us see what is the length of unique of S. 98. So out of 150 observations, so many got repeated. Okay. Then I'll have F star and B mat. bmat I need to run this part. Okay, capital bmat equal to capital B, and let me plot the first column, that is distribution of beta knots. Beta knots are like this. A histogram would give me a better idea, and in beta 1 would like something like this. Okay, so from these I can get confidence intervals. So I can take quantile. In fact, I can apply to both columns of bmat. So apply bmat to quantile probe equal to 0.025 and 0.975. Okay, so for beta naught the quantiles are 0.977 and 1.18. For beta 1 the confidence interval is 2.12, 2.34. Okay, now we have to do the other way and see how the confidence interval looks like. So via epsilon, sampling of epsilons. So most of the things I can copy from here. We'll change a few things. Okay, so I've got bmat, I've got x, fine. Now here, okay, I need to first compute fitted values and then residuals from the original model. So fitted of f would give me y hats. In fact, you can get residuals directly also, but anyway, now I've got fitted values, so residuals will be y minus y hat. So now what I have to do? See here, instead of drawing an arbitrary sample from 1 to n, we will draw sample from residuals of size n. X star we are going to use x, and y star I would use b naught. These are my notations, right? My estimated, yeah, b naught and b1. So b naught plus b1 into x plus s. S is my new residuals. So y star would be kind of new y hat with new residuals. Okay, everything else remains the same. In fact, we'll again check these histograms and the quantiles. I should call it bmat 1 so that later I can compare. Okay. Okay, so let me print the original thing also here so that it's comparable. See, there is a slight difference in the confidence intervals. Here this is 0.93, 1.23, and this is 0.97, 1.18, and here 2.13 became 2.12, 2.33 became 2.34. Okay, now I have some homework for you. I am not going to do the entire regression thing. You have to go home and do a further job. You have to check coverage. Okay, so for doing coverage probability, for estimating coverage probability, I need to know the actual values, so I can't do it on iris data. Okay, so let me describe the homework, and I could send you a sheet, but I want to explain the procedure because some of you may not understand the procedure on your own. So your job is to compare coverage probabilities. Okay, compare coverage probabilities of confidence intervals obtained via classical and bootstrap method. This is main homework. Okay, I'll explain the exact thing that I want you to do. classical and bootstrap methods in regression. So what you have to do? So take, say, beta naught equal to 2 and beta 1 equal to 3, something like this. So now your model is y equal to beta naught plus beta 1x plus epsilon, take sigma square equal to 1 maybe. So first generate x randomly from, say, uniform 0 1, okay, and then generate y via this method. So you can first generate epsilons from normal 0 1 and then compute y via this. So you have your data xy. So you'll have x1 y1, x2 y2 go up to 100, x100 y100. Once you have 100 pairs, forget that you know anything about beta naught, beta 1 or sigma 1 square. Now you have to rely completely on your estimation and bootstrap procedures. So first thing what you have to do, estimate beta naught, beta 1 and get confidence interval. Okay. Second thing you have to do is, this confidence interval is by your usual regression setup. Okay, so this is classical. So I think you can get directly in R. Second is estimate beta naught, beta 1, do non-parametric bootstrap by sampling from pairs, non-parametric bootstrap via pairs and get CI. Okay, let me call this as CI1, let me call this as CI2, and similarly do non-parametric bootstrap via residuals sampling with replacement from residuals and get CI3. Okay. Now, because this is a simulation exercise, you know that your actual beta naught and beta 1 are these. So you can check coverage probability. So first you check whether CI1 for beta naught contains 2, CI1 for beta 1 contains 3. Repeat that for CI2 and CI3 and record. Okay. Now you have to repeat this entire exercise. So starting from sampling till getting CI, this entire exercise you have to repeat 1000 times. Okay. So you'll get 1000 confidence intervals and then finally compute P1, P2, P3 for beta naught as well as beta 1. So what is P1? Proportion of times my first confidence interval contains 2. Then P1 for beta 1 is proportion of times my first confidence interval for beta 1 contains 3, and so on. So you get 6 such numbers. Okay, and see which at least in this setup, which confidence interval does the good job. Good job means ideally these proportions should be as close to 95% as possible. Okay, so try this. Those who have computer, try this and maybe if possible report the values to me. Okay, so today I will stop here. Think about it, bootstrapping, parametric bootstrap and then bootstrapping regression setup. Try to do this exercise, and just to get familiar with the technique, maybe try some toy exercises where you take only say 3-4 observations and then do the bootstrap thing manually. Okay, so I'll stop here. Thank you.